You keep hearing about going back to the Moon, then onto Mars, but almost never about going to Jupiter, and there is a very specific reason for that. If you personally signed up for a mission to Jupiter with today's technology, you would not be promised a way home. In this video, you are going to see step by step why the moment you aim yourself at Jupiter, the idea of a safe round trip starts to fall apart. So what is it about Jupiter itself that turns a return ticket into a fantasy? Start with the basic physical facts. Jupiter is about 11 times wider than Earth. If Earth's diameter is about 12,700 kilometers, Jupiter's is about 143,000 kilometers. In mass, Jupiter is more than 300 times heavier than Earth, even though it is mostly hydrogen and helium. That huge mass packed into that radius gives you strong gravity at the cloud top, about 2.5 times Earth's gravity. If you weigh 80 kilograms on Earth, you would feel like 200 kilograms there. In pounds, a 175-pound person would feel like around 440 pounds. You could still move, it would be hard but not immediately deadly. 2.5 G is within what the human body can tolerate for short periods. That sounds harsh but not hopeless. The catch is, the local gravity number is not what decides whether you can leave. The real barrier is the speed you must reach to escape. Here is the key twist. The difficulty of leaving a planet is not set by how heavy you feel standing there. It is set by the escape velocity, the speed you need to break free from that planet's gravity without needing more thrust later. On Earth, that speed from the surface is about 11.2 kilometers per second, around 25,000 miles per hour. Our rockets work very hard just to give a small spacecraft that the speed, and even then, they use staging, they throw away empty tanks, they push engines to their limits. By the time you're in low Earth orbit at about 7.8 kilometers per second, you only need a few more kilometers per second to be free of Earth. Now look at Jupiter. At the level of the visible cloud tops, the escape speed is about 60 kilometers per second. That is more than 5 times Earth's escape speed. In miles per hour, that is roughly 134,000 miles per hour. So the gap is not a small bump. It is a wall, and rockets do not handle that kind of jump gracefully. Because they carry their own propellant, the extra speed you want forces you to carry much more fuel, which makes your ship heavier, which then requires even more fuel and so on. The fuel demand grows faster than the speed you ask for. Going from 11 to 60 kilometers per second does not multiply your fuel needs by 5, it can blow them up by an order of magnitude or more, until almost everything you launch is just fuel to lift fuel, with the crew as a tiny payload sitting on top. If the problem was only that escape speed, you might still say fine, we will accept a giant absurd rocket and brute force our way out. But Jupiter does not just have high escape velocity, it also wraps that gravity in a set of conditions that directly punish every attempt to design a round trip. Around Jupiter, you have radiation belts far more intense than the ones around Earth. Jupiter's magnetic field traps high-energy particles and slams them through the space near the planet. Unprotected humans in some of those regions would receive a lethal dose of radiation in minutes to hours. Your spacecraft electronics would slowly degrade or suddenly glitch. To survive, you need heavy shielding, which means more mass, which then demands more fuel. Jupiter's surface is not a solid floor, it is just the depth in the atmosphere where the pressure is similar to Earth's sea level. Below that, pressure and temperature climb continuously until materials, seals and structures fail. There is nowhere solid to land, build and refuel. On top of that, at about 5 astronomical units from the Sun, sunlight is about 1/25 as strong as it is near Earth. Solar panels that are reasonable in Earth orbit become huge heavy arrays for the same power level near Jupiter. So now your ship needs nuclear power, big radiators for waste heat, more complex systems that must all survive for years. At this point you might ask, if physics does not forbid it, why call it impossible? Why not say just very hard? On paper, nothing in the laws of motion says you cannot dive near Jupiter and then climb back out. The equations are symmetric. If you can fall in, you can in theory reverse the process by adding enough energy. But when mission designers plug realistic numbers into the same planning tools they use for real spacecraft, the picture changes. The basic rocket rule that ties together your total speed change, your exhaust speed, and your starting and ending mass tells you that as you demand tens of kilometers per second of total speed change, your starting mass grows exponentially compared to your dry mass, the mass of the ship without fuel. For chemical rockets, the effective exhaust speed is only a few kilometers per second. To get 60 kilometers per second of total speed change, plus the extra needed for all the other maneuvers, the starting mass could be tens or hundreds of times larger than the mass of the actual ship and crew. Then you stack on thick radiation shielding, multi-year life support, structural strength to handle 2.5 G and possible high G maneuvers, and redundancy for every critical system. With rockets we can actually build and launch from Earth. You end up with designs that are too heavy to leave Earth, or too fuel-starved to escape Jupiter once they arrive, or too fragile to survive that environment for years. And the most troubling part is, this is only the first layer of the problem, focused on the gravity well and the local environment. You still have not paid the entry fee of getting there in the first place, the huge distance between Earth and Jupiter, and the extra speed changes needed just to match Jupiter's orbit around the Sun. When you add those travel costs on top, how much worse does the one-way bias become? So Jupiter's gravity well already looks bad, but here's the next problem. How much of your return ticket do you burn up before you even get there? The distance alone is brutal. The gap between Earth and Jupiter is not a fixed number. It changes as both planets move around the Sun. At the best alignments, you are looking at roughly 588 million kilometers, around 365 million miles. At the worst common alignments, the distance stretches to around 968 million kilometers, close to 600 million miles. That is one way. With the efficient transfer paths we know how to use, called Hohmann transfer orbits, a one-way cruise with current chemical propulsion sits in the range of about 6 to 9 months. That one leg, just outbound, already takes more calendar time than a full round trip to Mars with today's style of mission. And to get that trajectory in the first place, you have already spent a lot of propellant to escape Earth and line up with Jupiter's orbit speed around the Sun. So what are you really paying in speed terms, just to put your ship in front of Jupiter's face? Space engineers track this with a number called delta V, literally change in velocity, measured in kilometers per second. Think of it as your total speed budget. Every major maneuver, every time you fire the engines in a serious way, you spend some of that budget. From Earth's surface to low Earth orbit, you need roughly 9.4 to 9.7 kilometers per second of delta V. From low Earth orbit out to a path that escapes Earth's gravity and heads into deep space, you need on the order of another 3.2 kilometers per second. That second push is what sends you outward, on a curve that will intersect Jupiter's orbit months later. Then once you are in solar orbit on the way, you still need several more kilometers per second to match Jupiter's own motion and actually be captured into its neighborhood in a controlled way. If you want to insert into orbit around Jupiter instead of just flying past, you must burn again, hard, to slow down relative to the planet. Later, if you ever plan to leave, you will need another huge burn to climb back out of Jupiter's grip and then still more delta V to shape a trajectory back to Earth. Before you even count the 60 kilometers per second escape speed from low Jupiter orbit, your total delta V budget for a crewed round trip is already massive. Here is where the mission starts to become unrealistic. The relationship between that total speed budget and the fuel you need is not gentle. It is exponential, not linear. In simple words, if you ask for twice the delta V, you do not need twice the fuel, you can easily need several times more. The basic rocket rule that connects your starting mass, your ending mass, your exhaust speed, and your delta V shows that as you chase higher and higher total velocity change, the ratio of full rocket to empty rocket explodes. For chemical engines, the exhaust speed is only a few kilometers per second, maybe 3 to 4.5 kilometers per second, depending on the design. That low exhaust speed means you need a large mass of propellant to get even moderate total speed changes. For a modest crewed vehicle staying near Earth or going to Mars, you might be talking about a few hundred tons on the launch pad, which is already a big rocket. Now scale the delta V up to cover a full Jupiter round trip with all the burns we just listed, plus margins for safety, and your required propellant mass jumps into the tens of thousands of tons. You're no longer looking at a single heavy launcher. You're looking at an entire stack of very large rockets feeding one mission, just to move enough fuel. There is another hidden cost here that makes a return to Earth even less realistic. Every kilogram you bring along has to be accelerated over and over again. When you plan a true round trip, not a one-way stunt, you're not just sending a small capsule. You need a habitat with enough volume for humans to live for years, radiation shielding, robust life support hardware, spare parts, scientific equipment, and on top of all that, the propellant you will need for the trip home. Every single kilogram of that mass has to be launched out of Earth's gravity well first, then pushed onto the deep space trajectory, then slowed down to match Jupiter, then lowered into the Jovian system, then accelerated again to escape Jupiter, and finally steered back toward Earth. In imperial terms, the total mass easily runs into many millions of pounds when you add it all together. Rockets also get less efficient as they grow, and as you push them closer to their performance limits, so the more mass you add, the more you pay in extra structure and engine complexity, which adds even more mass. It is a feedback loop that pushes against you at every step. All of that is for a mission that, on paper, still insists on bringing everything back. For destinations closer to Earth, like the Moon or even Mars, this fight is rough, but we can just about see ways to win it. The delta V ladder is shorter, the travel times are shorter, the mass you need for life support and safety stays within the reach of large but realistic rockets. Once you push the target out to Jupiter, the combination of distance and required speed change makes the mass spiral so extreme that it starts to bend every sensible design towards something else. Engineers who run the numbers seriously do not end up with land on Jupiter and come back. They end up with mission plans that say stay in orbit only and never go deep, or send only robotic probes, or if humans go, they stay on a moon and do not plan to return soon, if at all. The physics punishes any attempt to carry the extra propellant for a full there and back, especially when you remember that all the fuel for the return burn has to be lifted, moved and stored during the entire first half of the mission. So by the time your ship finally reaches Jupiter's neighbourhood, you've already spent a huge amount of energy, burned enormous amounts of fuel, and locked yourself into a mass and speed situation that is hard to reverse. And this is all before you truly feel Jupiter's own gravity closing around you. The question now is simple and harsh. Once you start falling into the giant's well, with that limited fuel and that heavy ship, how do you ever climb back out? You might think that once you have spent months getting to Jupiter, you can just slow down a bit and park somewhere near it. But that is not how orbital mechanics works. In space, you almost never fly in a straight line the way a plane does in air. You're always falling along curves set by gravity. To meet Jupiter at all, your path around the Sun has to be reshaped so that your orbit crosses Jupiter's orbit at the right place and at the right time. That is already a carefully planned fall. When your ship finally reaches the area where Jupiter dominates the gravity, you are not gently arriving. You are diving into the deepest gravity well of any planet in the solar system, and from that moment, every move you make is about how much of that fall you can still control. The key detail here is that you do not come in slow. By the time you reach Jupiter, you're moving at tens of kilometers per second relative to the planet, not a few hundred meters per second. The Juno spacecraft, for example, approached Jupiter at around 60 kilometers per second, that is about 134,000 miles per hour, before it fired its engine to slow down and be captured. At that speed, there is no option where you just pull up, look around and choose a parking spot. Either you fire a huge braking burn, spending a massive amount of fuel to cut your speed, or you fly past Jupiter in a fast slingshot and you are gone, maybe forever. The maneuver to enter orbit is more like an emergency stop from highway speed on ice than a gentle stop at a traffic light. Small mistakes in timing or engine performance mean you either miss the planet completely, or you dive too low and risk hitting the atmosphere or the high radiation zones. Once you actually manage to lose enough speed to be captured into orbit around Jupiter, another important shift happens. Your orbital energy relative to the planet goes negative. In simple language, that means you are no longer just passing by, you are gravitationally bound. You do not have enough energy to drift away on your own. To escape again, you have to add energy back by burning engines in the right direction at the right time. The closer you drop toward Jupiter, the more negative that energy becomes, and the harder it is to climb back out. A high, loose orbit around the planet demands less escape speed, but leaves you further from anything interesting. A low, tight orbit lets you study the planet or its moons in more detail, but it also means you owe more and more energy later if you ever want to leave. Every time you trade fuel to go deeper into the system, you're also increasing the bill you have to pay to get out again. You might think then, fine, we will use gravity to our advantage, the same way we do to get to Jupiter in the first place. On the way out from Earth, mission planners often use gravity assists, flying close to planets like Venus or Earth again, to steal a bit of their orbital energy and redirect the spacecraft. Those maneuvers can save hundreds of meters per second or even kilometers per second of delta V, and that saves a lot of fuel. But that trick works best when you are still mostly in the sun's gravity, far from being tightly bound to a single planet. Once you're deep inside Jupiter's gravity well, the situation changes. There is no larger planet nearby to slingshot around. Jupiter is the big one. You can try to use its moons for small boosts, but those are minor adjustments compared to what you need to fully escape. You also cannot get a super assist from the Sun without first doing the hard work of climbing back out of Jupiter's control. The same orbital mechanics that let you fall in with clever assists do not give you an easy code to unlock a cheap escape after you have braked into orbit. This is where robots and humans diverge completely in how much risk you can accept when you play with these high-energy moves. Uncrewed probes like Galileo and Juno can use aggressive strategies to get captured. They can skim through Jupiter's upper atmosphere to slow down, a method called aerobraking, or, in more extreme versions, aerocapture. They can thread through the magnetic field in paths that minimize radiation only to a point, and they can accept that electronics will slowly degrade from accumulated damage. If a burn is slightly off, or a sensor glitches, and the probe ends up in a bad orbit or on a path that slams it into Jupiter, it is a loss for the mission team, but the risk was acceptable from the beginning. The spacecraft was always expendable. For a crewed ship, that tolerance disappears. Every major maneuver near Jupiter has to be designed with much bigger margins, because the cost of a mistake is not losing hardware, it is losing people. A slightly underpowered burn can leave you stuck in a stretched, highly elliptical orbit that crosses intense radiation belts again and again, dosing the crew and damaging systems. A timing error can make you miss the narrow window where your escape burn lines up with a path back to Earth, forcing you to wait months or years for the next alignment, while your supplies and hardware slowly run down. Too deep a pass near the planet and you risk an unplanned dip into the atmosphere, or into high-density particle regions that your shielding cannot handle. The orbital dynamics around Jupiter are unforgiving. Small differences in speed or angle at tens of kilometers per second quickly turn into huge differences in where you end up hours or days later. When engineers run simulations of these trajectories for human missions, they see a clear pattern. The paths that are cheap in fuel and time are narrow and risky, suited for robotic probes that can die at the end of the mission. The paths that give the crew wider safety margins require much more delta V, which means much more propellant, which blows up the mass of the ship, which makes the original problem of leaving Jupiter even worse. It is not just that Jupiter's gravity is strong, it is that the orbits that thread safely through that environment with human-level risk tolerance are extremely expensive in energy. So you end up in a trap. The more you try to make the orbital path safe for humans, the more fuel you need, and the more fuel you need, the harder it becomes to ever climb back out of Jupiter's gravity well. And that brings up the next hard question. If your whole mission depends on carrying and burning huge amounts of fuel perfectly, What does the core rocket physics say about how much propellant you really need, and where does that finally make the round trip break? Here is where the numbers stop being just big and start being no, this does not close. The basic rocket rule itself fights your return from Jupiter. There is a simple relationship that every rocket designer lives with. It says in words that the total speed change your ship can achieve is equal to the exhaust speed of your engine multiplied by the natural logarithm of the ratio between your starting mass and your final mass after his fuel is burned. That ratio is full rocket divided by empty rocket. For chemical engines, the exhaust speed is only on the order of 3 to 4.5 kilometers per second, roughly 7,000 to 10,000 miles per hour. That is not negotiable without changing technology. Now, when you plug in the kind of total speed change you need for a Jupiter mission, especially the 60 kilometers per second you would like available to escape from low near Jupiter orbit plus everything else, that mass ratio blows up. The math is unforgiving. If you want huge delta V with low exhaust speed, your rocket has to start out mostly as propellant. So what does that look like in actual hardware, not just in symbols? Take a dry mass, meaning everything that is not fuel, of 100 tons. That includes the structure, engines, tanks, life support, crew quarters, radiation shielding, and the crew and their gear. 100 tons is already a serious spacecraft, about 220,000 pounds. If you want that ship to have roughly 25 kilometers per second of total speed change using chemical propellants, you're already talking about thousands of tons of fuel. Not a few hundred tons. Thousands. That is millions of pounds of propellant for a ship that weighs only a couple 100,000 pounds empty. Now push that target closer to 60 kilometers per second to give yourself some hope of climbing back out of Jupiter's gravity well after all the earlier burns. The mass ratio you need starts to become absurd. You need so much propellant that, effectively, the payload of your mission is not the crew, it is the fuel needed to move the fuel stacked in layer after layer. At this point you might say, we already solved hard problems with staging, so why not just add stages until it works? Staging is the trick where you drop empty tanks and engines as you go, so you do not carry dead weight. That is how we make launches from Earth possible at all. But for a Jupiter round trip, staging does not magically remove the core issue, it just spreads it out. You would need an ultra-complex architecture with many stages, maybe assembled in Earth orbit, maybe with fuel depots scattered through deep space. Each stage is another set of tanks, engines, plumbing and control systems, all of which can fail. And even with perfect reliability, the fundamental pattern does not change. Most of what you are launching, maneuvering and trying to protect around Jupiter is just fuel to move other fuel. The actual habitable section for humans is a small fraction of the total mass you have built and shipped across the solar system. Then there is the obvious next idea: stop relying only on chemical rockets. What if you switch to higher energy propulsion? Nuclear thermal rockets, for example, could heat hydrogen to very high temperatures and push the exhaust speed up to maybe double that of chemical engines. Electric propulsion, like ion engines or Hall thrusters, can reach exhaust speeds of tens of kilometers per second or more. These options absolutely help. Doubling the exhaust speed makes the required mass ratio much smaller for the same delta V. High exhaust speed means you get more speed change per kilogram of propellant. But there are catches. Nuclear thermal still uses reaction mass and still has to carry its fuel. Electric propulsion has very high exhaust speed, but extremely low thrust, which is fine for slowly spiraling out of Earth orbit or nudging a robotic probe, not fine for fast, high G burns needed near a deep gravity well. And both options demand heavy reactors or power systems, long-lived hardware, and big radiators to dump waste heat. So even if you adopt them, the basic fact remains: dragging a human-rated, shielded vehicle from deep inside Jupiter's gravity out into free solar orbit still takes an enormous amount of energy. Our current and near-term engines can reduce the pain, they cannot erase it. So could you build a kind of nested, refuel-as-you-go super architecture, with depots and tankers staged all the way from Earth to Jupiter and the back. In theory, yes, you can sketch such plans. In practice, each depot, each tanker, each transfer adds yet another layer of complexity, cost and potential failure. You also have to launch and assemble all of that infrastructure before the first crew even departs. And remember, all of that hardware is sitting in space, aging under radiation and thermal cycling for years. By the time your Jupiter crew needs the fuel from, say, a distant depot, you have to trust that the tanks, valves, lines, control systems, and docking interfaces are all still working perfectly. The more you lean on this kind of chain, the more any single weak link can trap your crew far from home with no realistic backup. This is why when mission designers run realistic numbers instead of just writing concepts on a whiteboard, the result almost always backs away from the idea of touching Jupiter with humans. The focus shifts. Instead of planning a descent deep into Jupiter's atmosphere and then a climb back out, the scenarios become flyby-only missions, where you use Jupiter to bend your path and collect data as you pass. Or they become orbit-a-moon missions, where you settle into a more reasonable gravity well, like Callisto or Ganymede, and accept that the giant planet itself stays out of reach. Any architecture that includes going down deeper into Jupiter's gravity well and then trying to come back becomes a fuel monster. A design that is dominated by propellant tanks and energy budgets that do not fit inside any sane launch capability we have. The key point is that the rocket relationship is not a guideline you can argue with. It is a physical law. The numbers do not care that you really want a round trip, or that your storyboards show astronauts diving through Jupiter's clouds and then heading home. Once you demand huge total speed changes from engines with limited exhaust speed, the only way out is exponential mass growth or radically different propulsion physics. Until that physics is real hardware, the honest answer from the rocket equation is simple. If you send a human-rated ship down into Jupiter's gravity well with today's technology, you should treat that vehicle, and almost certainly that crew, as not coming back. And there is another reason this fuel wall is even worse than it first appears. The heavier you make the ship with all that propellant, the more shielding you need to protect it from Jupiter's intense radiation, and the more that shielding itself adds to the mass that the rocket equation punishes. So what happens to your already broken fuel budget when you now include the fact that space around Jupiter is not just deep in gravity, it is also one of the most lethal radiation environments in the solar system? How bad can space radiation really be if astronauts already live on the ISS for months, right? Around Jupiter, that experience does not help you much, because the main threat there is not vacuum or cold, it is an invisible particle storm driven by the planet's magnetic field. Jupiter's magnetic field at the cloud tops is roughly 10 times stronger than Earth's, and it extends millions of kilometers into space. It acts like a giant trap for charged particles from the solar wind and from Io's volcanic eruptions. Those particles get accelerated to high energies and jammed into belts around the planet. Radiation belts that are far harsher than Earth's Van Allen belts. This is not a small extra risk you just manage with a bit of shielding. This is a lethal environment that chews through electronics and human tissue. So how do we know it is really that bad and not just a scary model? Because we already sent hardware into that environment, and it got hammered. The Galileo spacecraft, which orbited Jupiter starting in the mid-1990s, carried significant radiation shielding and flew carefully planned paths, and it still suffered serious radiation damage. Its instruments glitched, memory bits flipped, and subsystems had to be reset or put into safe mode more than once. Later, the Juno mission was designed with this danger front and center. Juno's sensitive electronics are packed inside a titanium vault weighing close to 200 kilograms, about 440 pounds, whose only job is to cut down the radiation dose. Even with that, Juno's mission life is limited by radiation, not by fuel. Near the orbit of Io, one of the innermost large moons, the dose rates are so high that an unprotected human would take a fatal hit in minutes to hours, not weeks. The raw dose numbers are where your mission plan starts to crack. For humans, a whole body dose of around 4 to 5 sieverts, that is 400 to 500 rem in older units delivered over a short period, is enough to be lethal for many people. Around Jupiter, in some of the intense belt regions, dose rates can reach several sieverts per day. That means you could cross the lethal line in a day or two without serious shielding. even if you wrap the crew area in thick material, tens of centimeters of aluminum or an equivalent thickness of water or plastic, you only push the dose down, you do not make it vanish. Over weeks and months, the dose adds up. So if your plan involves staying in Jupiter's system for months or years, operating in orbits that cut repeatedly through those belts, the radiation budget pushes you into smaller and smaller safe windows. You cannot just hang out near Jupiter the way you can in low Earth orbit. The environment forces you to keep moving and to get out of the worst zones quickly. You might say, fine, we will add more shielding and buy back time. Thick walls of water, polyethylene, or specialized materials can block a lot of charged particles. That is technically true, and for robotic missions we already use heavy shielding around critical electronics. But for a human ship, every extra ton of shielding is another ton that has to be launched from Earth, accelerated into deep space, braked into the Jovian system, and then accelerated out again if you ever want to come home. If you decide the crew needs, say, an extra 20 tons of water around their habitat as a protective shell, that is about 44,000 pounds added to your dry mass. The rocket physics we talked about earlier then punishes you, because more mass means more fuel means bigger tanks mean more structure, and the loop continues. To make radiation levels tolerable for a long stay, your total mission mass can skyrocket into the range where your rocket is almost entirely shielding and propellant, with a tiny living space buried inside. And shielding is not just numbers on a spreadsheet, it changes the entire design. You want the crew as close to the center of mass as possible, buried inside a thick shell, which makes your vehicle bulky and harder to spin for artificial gravity. You need to route cables, plumbing, and life support through or around that shield, and you need to make sure maintenance is possible without exposing the crew too often. Every time you cut an opening, add a window, or attach a docking port, you create a weak point in your protection. So you end up adding even more material to cover those weak points, which again adds mass. All of that extra structure and complexity must then survive launch, the deep space cruise, and the violent maneuvers near Jupiter without failures for years. Put all of this together and look at what it does to your timeline. To keep the crew alive, you're forced into flight plans that skim the worst regions, spend minimal time near Eo's orbit or deep in the belts, and maybe try to use the shadow of a moon like Europa or Callisto to cut down exposure. That means you are flying fast, in carefully chosen paths, with almost no spare margin. A relaxed, slow mission, where you park in a convenient orbit, take your time, and then decide when to leave is not compatible with these dose limits. Instead, any human plan turns into a get in, do the minimum, get out immediately profile. That style of mission has to be synchronized with orbital mechanics, fuel limits, power limits, and hardware reliability. If one of those pieces slips, you can be forced to stay longer in higher radiation than you planned, and your safety margin disappears. For probes, this is annoying but manageable. You design the electronics to take a certain total dose, you accept that after a few years things will start to fail, and you schedule your science accordingly. For a crewed round trip, that mindset does not work. You cannot tell a human crew, our ship is going to be half dead from radiation by the time we need to fire the engines to come home. Let's hope it still works. So, realistic plans try to avoid exposing humans to the worst of Jupiter's radiation at all. That means most serious proposals either keep people far away, on safer moons and in higher orbits, or they leave Jupiter operations entirely to expendable robots while humans stay much closer to Earth. So now the picture is even worse than before. You already had a massive fuel problem, and when you add the radiation environment, the only way to make it survivable is to add heavy shielding that makes your fuel problem even bigger, and to compress your operating timeline into a narrow, high-risk window. For a crewed mission, that's a strong push away from stay, explore, and then return, and toward do not go at all, or if you go, do not promise to bring anyone back. And that leads straight into the next brutal constraint. Even if you beat gravity and radiation, what are you actually landing on and leaving from, when Jupiter does not even give you a solid surface? You keep hearing Jupiter is a gas giant, but what does that actually mean for a landing or a takeoff? for a real mission that wants to go down and then leave again? On Earth or Mars, you can at least aim for rock. On Jupiter, there is no solid ground you can use. The surface people talk about is just an invisible layer in the atmosphere where the pressure is about 1 bar, the same as sea level on Earth. Above that, the gas is thinner. Below that, it gets denser and hotter, and it transitions smoothly from gas to something more like a super-compressed fluid. There is no hard floor where you can park a lander, no bedrock to bolt equipment to, no stable platform where you can build a propellant plant and refill your tanks. If you send a ship down, you are sending it into an endless, thickening atmosphere, not toward a landing pad. So what happens if you just try to float instead of land, like a balloon? That is where pressure starts to kill the idea. At around 10 bars, the pressure is like being 100 meters under Earth's oceans. At around 100 bars, think of the deepest ocean trenches where only the strongest submersibles can survive. Go deeper in Jupiter, and the pressure keeps climbing, up into hundreds of thousands of bars and then into the range of millions of atmospheres. No known structural material can hold a human habitable interior against that kind of external pressure for long. The hull would have to be unbelievably thick and strong, and even then, small flaws would grow into cracks. In practical terms, your ship's structure would fail long before you reached any kind of solid interior, assuming such a thing even exists in a form you could stand on. And it's not just pressure. The temperature profile makes it worse. Near the visible cloud tops, temperatures are around minus 145 degrees Celsius, roughly minus 230 degrees Fahrenheit. That is already extremely cold. But as you descend, the temperature rises steadily. Deeper down, you hit hundreds of degrees, then thousands, eventually getting to values comparable to the surface of the Sun, in the thousands of degrees Celsius. So your hull and your systems have to handle a climb from extreme cold to extreme heat without losing integrity. Electronics, structural alloys, seals, lubricants all have operating ranges. You would be asking them to survive conditions more brutal than Venus, and Venus already has surface temperatures hot enough to melt lead and crush most landers within hours. Now combine that heat and pressure with motion. Jupiter's atmosphere is not calm layered air, it is a dynamic, violent fluid system. The winds do not just blow steadily in one direction, they shear. Wind shear means the speed and direction of the wind change rapidly with altitude. Jupiter's banded appearance comes from huge jet streams. Some winds blow over 100 meters per second, about 225 miles per hour, and they wrap around the planet. Add in storms like the Great Red Spot, which is larger than Earth and has wind speeds in the hundreds of kilometers per hour range, and you get a picture of an atmosphere that is constantly pushing and twisting anything inside it. A vehicle trying to climb back out would have to fight upward through layers of turbulence while also pushing against gravity and thickening air. The aerodynamic forces on the structure would be severe. To survive, you would need a very strong, very rigid design, and that means more mass, which makes your escape burn harder. You might think, then do a quick dip, don't go deep, just touch the clouds and come back up. But even that shallow dive idea runs into serious problems. First, you need heat shields strong enough to handle high-speed entry into a thick atmosphere while already moving tens of kilometers per second relative to Jupiter. Second, you need engines that can restart and push you back up against both drag and gravity, and they need to work the first time, every time. Third, the moment you cross into denser layers, you start losing control authority to turbulence and shear. You're not gliding in smooth air. You're fighting a chaotic fluid that can twist your vehicle, alter your angle of attack, and drive loads into the structure that your engineers did not predict perfectly. Any design strong enough to survive those forces, plus the thermal and pressure demands, becomes so heavy that carrying the fuel to lift it back out is completely unrealistic. Probes we have actually sent into atmospheres give a clear warning. The Galileo probe's atmospheric entry module dropped into Jupiter in 1995. It had a massive heat shield, and it still experienced extreme heating during entry. It transmitted data for under an hour before it was lost, likely destroyed by pressure, temperature, or both. On Venus, landers have survived for a few hours before succumbing to heat and pressure, and Venus is gentle compared to the deep layers of Jupiter. These are small unmanned vehicles, designed to push materials to their limits for a short, heroic lifespan. A human-rated ship cannot follow that model. You cannot plan a crewed mission where the vehicle is expected to survive for just an hour or two inside the atmosphere before failing. So if there is nowhere solid to land and the deeper atmosphere quickly moves beyond any realistic structural and thermal limits, what are you really planning when you say we will descend and then come back? You're proposing to send an extremely heavy, overbuilt, heavily shielded vehicle into a region where pressure and temperature climb to the point that any failure is catastrophic and rapid, where winds and turbulence push your structure and control systems to their limits, and where there is no platform to stop, repair or refuel. Even if you float for a while at some comfortable level, you still have to leave, and that means fighting your way back up through the same layers with the same risks while your structure and systems are already stressed and aged. When you look at all of this together, touching Jupiter stops looking like a bold exploration plan and starts looking like a controlled plunge with no credible path back out. Probes go in and die. A human mission cannot count on landing, fixing anything or making new fuel down there. Without a firm surface or a stable, manageable pressure region that you can use as a base, a deep dive into Jupiter's atmosphere is, practically speaking, a one-way move. It is something you might do with robots you're willing to lose, not with a ship that has to bring people home. And even if you say, fine, we will never go very deep, we will just skim the upper atmosphere, you are still dealing with an environment of powerful winds and planet-sized storms that do not stop. So what happens to your already fragile ascent plan when you add in the fact that Jupiter's weather is not just bad, it is a global, supersonic gauntlet that you cannot turn off or fly around? How do you fly a return rocket through an atmosphere that is basically an endless global storm system? Jupiter's clouds look smooth from far away, but up close the planet is covered in fast, organised jet streams. Those light and dark bands you see, the zones and belts, are not just colours, they are high-speed rivers of gas wrapping all the way around the planet. Some of those winds blow over 150 metres per second, around 335 miles per hour. On Earth, the jet stream is a narrow band you can sometimes avoid or cross at an angle. On Jupiter, these bands circle the whole world with almost no land to break them up. Any path you choose to enter or exit the atmosphere has to cut straight through layers of moving air that never really calm down. It gets worse when you look at the large-scale storms. The Great Red Spot is a single storm that is wider than Earth itself and has been active for at least 300 years. Wind speeds inside it reach roughly 430 to 680 kilometers per hour, about 270 to 425 miles per hour, and it is not the only structure like that. Jupiter is full of giant vortices, swirling ovals, and chaotic regions where different jet streams collide. If you are trying to bring a spacecraft back up from a descent, you are not threading through a clear sky with one storm to avoid. You're operating in an atmosphere where storm layer is the normal state. It is like flying through a permanent hurricane band that stretches around the whole planet. Think about what that does to a vehicle that relies on engines and control surfaces to stay pointed the right way. Even high-performance fighter jets on Earth avoid dense, chaotic weather when they can because wings, tails, and control surfaces have limits. In Jupiter's upper atmosphere, the air is thin, but as you descend, the density goes up, and the relative wind speeds between layers can become extremely high, even supersonic in places. For a rocket or lifting body vehicle trying to climb back out, that means you can have shock waves, violent buffeting, and sudden changes in aerodynamic forces. You're trying to push something heavy and relatively fragile, with chemical thrusters and limited steering authority, through conditions that would challenge even a much smaller, stronger machine. Now add in guidance and error growth. In a clear, stable atmosphere, if your angle of attack is off by a small amount or your thrust is slightly misaligned, you can correct slowly. In a turbulent, sheared flow, small deviations get amplified. A nose that pitches a few degrees too low can get grabbed by a downdraft or a shear layer and pushed deeper. A thrust vector that is a tiny bit off can turn into a sideways slide into a stronger jet stream. What began as a shallow, controlled entry can turn into a much deeper plunge. On the way back out, A carefully planned ascent corridor can be blown sideways into regions of higher drag or higher winds, forcing you to use more fuel than planned just to stay on path. When your margin between we have enough speed to escape and we fall back in and cannot try again is small, these atmospheric uncertainties do not just make the ride rough, they make the whole ascent plan unstable. And remember, every extra bit of fuel you carry to handle these surprises makes your vehicle heavier, which makes it harder to accelerate, which increases the time you spend in the dangerous layers. That extra time means more aerodynamic loads, more heating, and more chances for turbulence to shove you off the ideal track. You can try to oversize the engines and reinforce the structure, but that again adds mass, which pushes you back into the same loop. At some point, the design stops looking like a realistic spacecraft and starts looking like an overbuilt concept that cannot leave Earth in the first place. Because of this, when scientists and engineers model realistic mission profiles, the conclusion they keep reaching is straightforward. Keep crewed vehicles out of Jupiter's atmosphere entirely, stay in orbit, drop small disposable probes if you want local measurements, let them fall, transmit what they can, and accept that they will be destroyed. The core ship, the one that has to stay functional for years and then bring humans home, does not go down into the fluid gauntlet at all. The more we study the fluid dynamics of Jupiter's atmosphere, the less sense it makes to even talk about a reusable crewed craft that descends and then climbs back out under its own power. So at this point the picture is tight. The gravity wants to trap you, the rocket physics punishes your fuel budget, the radiation forces you to add heavy shielding, and the atmosphere turns any descent and ascent into a high-risk, low-margin maneuver. And we still have not touched the most extreme part of Jupiter's story, the region deeper inside where hydrogen stops behaving like normal gas and turns into something metallic, like something that might sound like a perfect power source, but in practice just locks your escape energy behind conditions no human ship can reach. Deeper inside Jupiter, the stuff you think of as simple gas stops acting like anything you have direct experience with. As you go down, pressure climbs from a few bars to hundreds to thousands, and then up into the range of 1 to 4 million times Earth's surface pressure. Temperatures go from minus 145 degrees Celsius in the upper clouds to thousands of degrees at depth. Under those conditions, hydrogen is squeezed so hard that electrons can move freely, and hydrogen starts to behave like a metal, a state we call metallic hydrogen. In that layer, hydrogen can conduct electricity very well, and that moving, conducting fluid is a big part of what powers Jupiter's huge magnetic field. So when you hear about Jupiter's magnetosphere and deadly radiation belts, a lot of that tracks back to this exotic deep interior region. From a distance, metallic hydrogen sounds like an opportunity. You might think if hydrogen turns into a metal down there, maybe we can use it as an amazing propellant, tap into it as an energy source and solve the fuel problem. The reality is, right now, we barely understand it at the scale Jupiter uses it. On Earth, we can only glimpse metallic hydrogen under extreme pressures in tiny lab samples, and even those results are debated. We have never created stable bulk metallic hydrogen that sits at normal pressure and temperature. That means we do not have solid, tested data on how it behaves when you have planet-sized amounts of it, how it flows over long times, how it carries heat, exactly how it couples to magnetic fields. For engineering, that level of uncertainty is a major red flag. You cannot base a critical mission system on a material whose large-scale behaviour you do not know well. Now compare those interior pressures to what our strongest structures can actually handle. The deepest places humans have sent crewed submersibles to on Earth's ocean floor sit around 1,100 bar, which is roughly 1,100 times Earth's surface pressure. That is already enough to crush most materials if they are not designed perfectly. Inside Jupiter, as you head toward the metallic hydrogen layer, the pressure is not 1,000 times Earth's, it is in the range of 1 million times or more. That gap is so huge that it is not just a bit harder, it is outside the range where our current materials and structural concepts even make sense. Any idea that involves deep platforms or machines that operate stably down in the metallic hydrogen zone is, with present-day technology, in the same category as faster-than-light drives. Interesting to think about, not something you put into a serious mission plan. Even if you had materials that did not instantly fail, the environment is still against you. At those depths, the combination of temperature and pressure means metals soften, electronic components fail, and any normal coolant boils, freezes, or breaks down chemically. You would be trying to run complex machinery in a place that constantly pushes every component past its safe operating range, and you would need that machinery to work for long enough to collect metallic hydrogen, process it, and raise it back up through layers that are themselves hot, dense, and turbulent. That is not just hard, it is many steps beyond any industrial system we have ever built. There is another catch that people sometimes miss when they get excited about metallic hydrogen. The energy density cuts both ways. In theory, metallic hydrogen could store enormous energy per kilogram and release it when it turns back into normal molecular hydrogen, making it an incredible rocket fuel with very high exhaust velocity. But to get that advantage, you first have to create it and then keep it stis. If it only exists at millions of atmospheres, it is like having a super battery that only works inside the core of a star. To use it, you would have to drag it up into conditions where it wants to explode back into a lower energy state. And you would have to control that process with precision. That is extremely dangerous. And remember, all of this is happening in a gravity well, where any hardware mistake sends your equipment falling deeper, not drifting away harmlessly. So from a practical standpoint, metallic hydrogen in Jupiter's interior is not your way out. It is a trap. The planet is holding an enormous amount of energy in a form you cannot access with any tool you can realistically build and survive with. You cannot reach it with crude hardware. You cannot keep it stable at low pressure. You cannot use it as a refueling source for a return rocket sitting up near the cloud tops. The power is there, but it is locked behind physical conditions that destroy your tools faster than you can even test them. That is why no serious mission design says, "We will go down, scoop some metallic hydrogen and use it to fly home." The return leg has to be powered by fuel you brought with you from Earth, or by fuel you can make in much gentler environments, like on the surface of an icy moon, where you can crack water into hydrogen and oxygen. The deep interior of Jupiter stays in the category of interesting physics, not usable infrastructure. Once again, the more you study it, the clearer it becomes that Jupiter is not just big, it is fundamentally not set up to help you leave once you commit to going in. And even if you give up on mining the interior and accept that all your fuel must come from outside, you still have a basic problem. You have to power your ship and keep your crew alive far from the sun, in a place where solar energy drops to a small fraction of what you're used to. So what happens to a mission that already has a fuel and mass crisis when you move it out to a region where sunlight is only about 1/25 as strong as it is near Earth? And every kilowatt of power becomes harder to generate and harder to get rid of as waste heat? How do you run a power-hungry ship in a place where the main power source of the solar system has almost faded out? By the time you're at Jupiter's distance, about 5 astronomical units from the Sun, sunlight is no longer the strong, bright resource it is near Earth. The solar flux there is roughly 1/25 of what we get in Earth orbit. That means if a 10 square meter solar array near Earth gives you around 3 to 4 kilowatts of electrical power, the same panel near Jupiter gives you only about 120 to 150 watts, roughly what a bright household light bulb uses. A crewed ship does not run on a light bulb. Life support, heating, computers, communications, guidance, and any electric propulsion you want all stack up to tens of kilowatts at the bare minimum, and realistically into the hundreds of kilowatts. To get that from sunlight at Jupiter, you would need solar panels with an area measured in thousands of square meters, comparable to the footprint of a city block, and those panels would have to be carried there and back out of Jupiter's gravity well. That is structure, mass, and complexity you do not want to drag into an environment that is already trying to crush and fry you. Real missions to Jupiter already show you where the practical line is. The Galileo probe did not even bother with giant solar panels. It uses radioisotope thermoelectric generators, RTGs, which convert the heat from radioactive decay into electricity. RTGs give only a few hundred watts each, but they work far from the sun and they are reliable over many years. Juno's the first Jupiter mission that pushed solar to its limits. with 3 huge panels more than 20 meters long each. That is fine for an uncrewed craft with low power needs and careful pointing. But scale up to a human mission. Now you need power for closed-loop life support, robust communication systems, heavy computing for autonomy, strong thermal control, and maybe high-efficiency electric thrusters to help with trajectory changes. Your power demand jumps far past what even Juno-sized solar arrays can handle at 5 astronomical units. At that point, you are pushed toward RTGS on a big scale or full nuclear reactors, with all the shielding, plumbing, and safety systems those require. Getting power is only half the job. You also have to get rid of waste heat, and that gets harder, not easier, as you go farther from the sun. In orbit around Earth, spacecraft can sometimes dump heat into the thin upper atmosphere or share loads with cooler structures. Near Jupiter in deep space, there is no air or water to act as a heat sink. The only way to cool your ship is to radiate heat away as infrared light from large radiator panels. For a reactor or a big electric propulsion system, that means hundreds of square meters of radiators, in imperial terms thousands of square feet, hanging off your ship like wings. Those surfaces must stay pointed in useful directions, they must not overheat, and they must avoid being shadowed by other parts of the spacecraft. They are also vulnerable. Micrometeoroids or debris can punch small holes in them, lowering their efficiency. Dust and small impacts over several years of flight slowly eat away at your cooling capacity. Now connect that to your escape plan. High-energy maneuvers, especially with electric propulsion or with reactors running at high output, generate a lot of waste heat. If your radiators are damaged or degraded, you may not be able to run your engines at full power without overheating your systems. That forces you to throttle down, which means lower thrust. Lower thrust means slower spirals out of Jupiter's gravity well and longer exposure to radiation, which we already know is a serious problem. A ship that left Earth with comfortable power margins can arrive at Jupiter with a power system that is weakened by age, damage, or both. If that happens, you might not have the sustained thrust to climb out on the planned timeline, or you might have to shut down non-essential systems to keep life support running, cutting into your navigation and communication capabilities. Power shortfalls do not only affect propulsion, they also hit life support directly. Air circulation, water recycling, CO2 removal, temperature control in the habitat, food production if you are using any kind of greenhouse, all depend on steady electricity. If your power system cannot meet demands, you're forced to choose between using power for crew survival now, or saving it for later burns and course corrections. With tight margins, you can reach a point where the safe choice for the crew in the short term makes the long-term escape physically impossible, because you have to give up or delay key maneuvers. Near Earth, this kind of degradation is serious but not fatal. If a station in low Earth orbit loses some solar panel output, crews can reduce activity, schedule repairs, or in worse cases, get into a capsule and come home within hours. On a lunar mission, if power degrades, you can still cut the stay short and burn for Earth. At Jupiter, there is no such quick exit. Every major power-carrying subsystem has to work almost perfectly for years. The reactor core or RTGs, the power management electronics, the radiator panels, the cabling, the motors that pivot arrays if you still use any solar, the control computers that regulate everything. A slow drift downward in performance can turn into a hard limit at exactly the moment you need maximum reliability for your escape sequence. From a planning standpoint, that makes Jupiter look very different from any destination near Earth. You cannot design a mission that assumes you will manage power problems on the fly or accept significant performance loss over time. You have to assume the ship will need nearly full capability at the end of the mission, when it is oldest, most damaged by radiation, and farthest from help. If you design for that, your power systems get heavier, your radiators get bigger, your shielding increases, and all of that pushes your mass and complexity up again, feeding straight back into the rocket and fuel problems you already have. So now the picture is this. You are far from the sun with weak solar energy. You are forced into nuclear-style power sources. You have to cool large, fragile radiators in a harsh environment, and you must keep that whole system near peak performance for years just to have a chance of leaving. That is not a comfortable margin, it is a knife edge. For decision makers, that turns a crude round trip to Jupiter from dangerous but possible into an experiment where one slow failure in the power chain can lock a crew into a place they can never leave. And even if you somehow keep the lights on and the engines running, you still have another big constraint that never goes away: time. A round trip to Jupiter is not a quick sprint. It is a multi-year mission where life support, human bodies and human minds have to operate under stress for 4 to 6 years straight. So what happens to your chances of ever coming home when you stretch every system and every person on board to that kind of timeline in a place that already gives you no safe abort? Even if you solve gravity, fuel, radiation, atmosphere and power, you still run into a quieter but deadly constraint: time. With the propulsion we actually have, a round trip to Jupiter plus time in the system is not a 1-year adventure. It is a 4 to 6 year commitment. You have roughly 6 to 9 months going out, some months of operations while the alignment with Earth is useful, then another long cruise back. That is longer than any continuous human stay off Earth so far. Every extra year in that timeline is another year for something to break, for someone to get seriously sick, or for the crew's mental health to slide. On the ISS, people rotate in and out. Cargo ships bring fresh supplies and parts, and if something goes badly wrong, you can be back on Earth in hours. At Jupiter, there is no rotation, no quick escape, and no resupply truck on standby. Look at the basics first: consumables. Even with aggressive recycling, humans need a baseline of water, oxygen, food, and spare parts. Before recycling, a single person can easily use a few kilograms of water and food per day, in the range of 3 to 5 kilograms, call it 7 to 11 pounds. Air is mostly recycled, but you still need filters and chemicals to scrub CO2 and other contaminants. Now multiply by, say, 4 crew members and then by 4 to 6 years. Suddenly you are talking about many tons of mass in food, water, backup gases, and replacement parts. You can reduce that somewhat with closed-loop systems. You can grow some food, you can reclaim water from waste, but you will never push the net requirement to 0. And because Jupiter is so far away, you cannot count on regular resupply. So all that baseline mass has to be carried from Earth, accelerated all the way to Jupiter, protected there, and then carried back out. Every ton of consumables is another ton the rocket equation punishes. Then there is the life support hardware itself. A truly closed-loop system is not a simple machine. It is essentially a small artificial ecosystem plus industrial chemical plant. On the ISS, the water recovery and air revitalization systems are complex racks of machinery that sometimes fail, leak, or need hands-on interventions. Filters clog, valves wear out, sensors drift, software glitches. Crews fix them, and if something is beyond repair, a new unit can be flown up from Earth. For Jupiter, you need life support that can run with limited intervention, minimal spare parts, and no external help for half a decade. If a major component fails in Jupiter orbit, and you cannot fix it with what you have on board, you do not have the option to come home early. You are many months and a big escape maneuver away from any return trajectory. A failure that would be an inconvenience in low Earth orbit can be a mission-ending, crew-killing event in the Jovian system. Now think about what this time does to the crew's bodies. In microgravity or low gravity, your bones lose density, your muscles atrophy, your heart and blood vessels adapt to not working against 1G. Astronauts on the ISS work out several hours a day just to slow this down, and after roughly 6 months they still come back weaker and need time to recover. On a 4 to 6 year Jupiter mission, you can try to use exercise and maybe rotating sections to simulate gravity, but you will not erase the effects completely. The crew that arrives at Jupiter and then finally reaches the return phase is not a fresh, fully conditioned team. They are people whose bodies have been slowly degrading, who have lived in confined, stressful conditions, perhaps with sleep disruption and constant low-level anxiety. Now ask those same people to handle emergency procedures, high G burns during critical maneuvers, and fast decision-making in a lethal environment. The return leg, the hardest part of the mission, demands peak performance from humans who may be at their physical and mental limits. Psychology adds another layer. Long-duration missions push people in ways that are hard to predict. Conflicts inside the crew, depression, anxiety, burnout, and simple fatigue build up over time. On Earth, or even in Earth orbit, there are escape valves. People can be rotated out, given breaks, supported by large ground teams with quick feedback. At Jupiter, signals take tens of minutes to go one way. Real-time support is gone. The crew must solve most of their problems themselves, with a delay before anyone on Earth even hears about them, let alone answers. Over 4 to 6 years, the odds that someone will hit a serious mental or emotional wall are not small. If that happens during a critical phase, like planning an escape burn or managing a system failure, the consequences can be fatal. When you lay the mission out as a timeline, it looks like this. A very long outbound cruise where systems slowly age and the crew slowly wears down. A relatively short high-risk operations phase in one of the harshest environments in the solar system, and then another very long cruise back, all under tight energy and power constraints, with almost no slack for major failures. Every extra piece of redundancy you add to reduce risk increases mass, which makes your propellant problem worse. Every attempt to cut mass to ease the fuel problem reduces your safety margin if something goes wrong. It is a constant trade between survivability and the ability to leave Jupiter at all. Taken seriously, this trade pushes you in a clear direction. The more you account for human limits, the more obvious it becomes that sending people on this kind of mission is stacking too many low-probability dangers on top of each other. The natural solution is to remove the weakest link in the chain, the human body and mind, replace the crew with hardened electronics, radiation-tolerant circuits, and robotic systems that do not care about bone loss, boredom, or the difference between a 2-year and a 6-year mission. Robots do not need air, water, or food. They do not need space to sleep or the windows to look out of. They can be smaller, lighter, and more tolerant of high radiation paths and aggressive maneuvers. That shift in thinking is important because it sets up the next problem, one that applies even before you decide who flies. With humans on board, navigation, communication, and the ability to abort are not just technical details. They are the line between dangerous but survivable, and one glitch and everyone dies. So what happens to your chances of ever coming home when light itself needs tens of minutes to carry a signal between you and Earth, and there is no such thing as a quick abort path if something goes wrong near Jupiter? By the time you reach Jupiter, even the speed of light is too slow to save you if something goes wrong. At that distance, radio signals take on the order of 30 to 50 minutes for a round trip, which means about 15 to 25 minutes one way. You send a message to Earth. They see it after that delay, they think, they answer. You get the reply another 15 to 25 minutes later. There is no real-time control. No one sitting at a console on Earth can joystick your ship out of a bad situation. If your navigation computer glitches during a critical burn, if a valve sticks, if a thruster underperforms, you have to detect it, diagnose it, and react on board, with no immediate help. For small corrections during cruise, that is fine. For a make-or-break maneuver near Jupiter, where seconds matter, it is brutal. Autonomy is not a feature here, it is a hard requirement. Now look at what that means for abort options. In low Earth orbit, if something serious breaks, you can usually deorbit within hours and be on the ground the same day. On a Mars transfer, you often have at least some flexibility. You can tweak your trajectory, cut the mission short, and aim for an earlier Earth encounter if you have the fuel. From Jupiter, once you commit to a particular transfer orbit, you are locked in for months or even years. The orbit you follow is determined by your speed and position when you leave Jupiter, and changing that significantly requires large amounts of delta buoy. If something goes wrong with your return burn and you miss the ideal departure window, there is no simple turn around and come home option. Any alternative path that gets you back faster or safer will demand extra speed, changes you almost certainly did not budget for. Most of the time, the choice becomes live with a much longer mission and hope your systems last, or admit that you do not have a realistic way back. The navigation side of this is just as unforgiving. Near a massive planet like Jupiter, small velocity errors add up fast. A burn that is off by just 0.1 meters per second, a tiny fraction of your total speed, can grow into a missed distance of thousands of kilometers months later. When you're trying to design an escape trajectory that threads between the orbits of large moons, avoids the worst of the radiation belts, and lines you up correctly for an Earth intercept years down the line, that sensitivity is dangerous. Your margin for navigational error shrinks. You need engines that deliver exactly the thrust you expect on exactly the schedule you plan. You need attitude control systems that point the ship with high precision. And you need those systems to perform like that after years of use, thermal cycling and radiation exposure. Hardware reliability becomes a life or death issue. Critical navigation and propulsion components, like star trackers, gyroscopes, reaction wheels, attitude thrusters, and your main engines have to work correctly for the entire mission. There is no service yard in Jupiter orbit. You cannot pull into a station, swap out an engine and try again. Any serious degradation near the end of the mission translates directly into, we cannot execute the return plan. If a star tracker dies, your ability to know your exact orientation drops. If a main engine develops a leak or loses performance, your escape burn may fall short of the speed you need. Redundancy helps, but redundancy costs mass, and mass is exactly what you're already fighting. Designing hardware to be that reliable, for that long, in that environment, drives complexity up and pushes cost and mass into ranges that are hard to justify. Think about simple examples. A gyroscope drifting a bit faster than expected can slowly poison your attitude solution. Over weeks, that bias in your orientation estimate can cause you to point your engine slightly off from the intended line during a major burn. You finish the maneuver thinking you are on one escape path, but you are actually on another, one that might intersect a moon or cross into a higher radiation region than you planned. With robots, this is a painful lesson and a lost mission. With humans, it is potentially the start of a slow failure that traps a crew in an orbit they cannot safely leave. On top of that, you have no quick way to test your lifeboat options at Jupiter. On the ISS, you always have a capsule ready to bring people down. You can check it, upgrade it, rotate it with newer hardware. On a Jupiter mission, your lifeboat is the same interplanetary ship that brought you there, plus maybe a small re-entry vehicle for Earth at the very end. You cannot afford to bring a second full capability return vehicle as backup. It would double your already impossible mass. So the one set of engines, tanks, guidance systems, and control computers you left Earth with has to carry you out, bring you home, and still be in good enough shape to handle re-entry or rendezvous when you reach Earth's neighbourhood again. This is why human missions always talk about an abort philosophy. For Apollo, there was a plan for nearly every phase of the mission to get the crew back alive, even if some major piece failed. For modern crewed launches, you have launch escape systems, alternate orbits, and multiple return paths. With Jupiter, truly safe abort paths barely exist. Once you're on the way, turning it into just come back now usually means adding large chunks of delta VI you did not plan for, which you cannot do without fuel you do not have. That is before you even consider timing issues with where Earth and Jupiter will be in their orbits when you try. Put all of these factors together: long light time delays, high sensitivity to tiny navigation errors, aging hardware that has to work perfectly during the most critical burns, and almost no realistic abort routes. For a robotic mission, you can accept that risk. You design the spacecraft to be as robust as you can, but you accept that one unlucky event can end the mission. For a human mission, that same risk profile is not acceptable. A situation where a single stuck valve or mistimed burn at the end of a 5-year trip can trap the crew beyond any help is very hard to justify. So mission planners look at Jupiter and see a simple conclusion. If you cannot offer a credible abort, if you cannot promise at least 1 or 2 backup paths to survival, when something fails, you should not send people. You send machines instead. Let them face the timing constraints, the guidance challenges, and the lack of abort options. They will not suffer if a course correction comes too late, or if a signal from Earth arrives 10 minutes after it was needed. And that leads to the next piece of the story: the machines we have already sent. Probes like Voyager, Galileo, and Juno have been into Jupiter's neighbourhood and, in some cases, right into its atmosphere. They showed us both what is possible and where the hard limits really sit. Once you see how those missions were designed and how they ended, the idea of a human ship going down into Jupiter's realm and coming back starts to look even more like fiction than engineering. The way we have actually flown missions past Jupiter already tells you how seriously we take its dangers. The first big visitors, Voyager 1 and Voyager 2, did not even try to stay. They came in on high-speed paths, took their pictures, measured fields and particles, then used Jupiter's gravity as a slingshot to head farther out. Those were gravity assist flybys, designed to pick up speed, not lose it. For a human mission that wants to come back, that exact kind of trajectory is what you do not want. You do not want to roar past at tens of kilometers per second with no way to brake. But notice the choice we made. We preferred quick, high-energy passes that never even attempt capture, because slowing down enough to orbit safely around Jupiter was already a major technical and fuel challenge, and that was just for small, uncrewed probes. When we finally did commit to staying with Galileo, the experience confirmed how hostile the environment is. Galileo entered orbit around Jupiter in 1995 and stayed for about 8 years. It was built with radiation in mind, thick shielding around key electronics, careful planning of its orbit to reduce time in the worst parts of the belts. Even so, its systems took repeated hits. Engineers saw memory bits flipping from radiation, instruments gradually degrading, and the spacecraft going into safe mode multiple times when charged particles triggered faults. Every one of those upsets needed analysis and recovery. That was accepted because Galileo was a robotic craft. If an instrument died early, it was disappointing, but not tragic. Now scale that to a human-rated ship with life-critical computers, life support controllers, engine controllers. The same radiation that scrambled Galileo's brain cells would be attacking the systems that keep your crew breathing and your engines pointing the right way. Juno pushed the design even further. It launched in 2011, reached Jupiter in 2016, and was built with the clear expectation that radiation would try to tear it apart from day one. Its orbit is polar, going over the planet's poles instead of looping around the equator. That path is chosen to dodge the worst of the radiation belts, which are stronger around the equatorial region. On top of that, Juno's main electronics are not spread around the spacecraft. They're concentrated inside a titanium vault about 1 centimeter thick, weighing around 200 kilograms, roughly 440 pounds. That vault is there purely to block radiation. Even with that, the mission has a planned finite life determined by how much damage the electronics can take before they are no longer trustworthy. Now, think about a human ship. You would need similar or better protection around a much larger internal volume, not just one electronics box. You would need shielding around habitats, control rooms, backup computers, and the network that connects them. The mass of that shielding would be far greater than Juno's vault, and all of it would have to be hauled in and out of Jupiter's gravity well. Then look at how we end these missions. Galileo was not left in orbit to slowly die. In 2003, controllers deliberately sent it into Jupiter's atmosphere, where it burned up. The same will eventually happen to Juno. Officially, we do this to avoid the small but real chance of contaminating moons like Europa or Ganymede with Earth microbes. But this choice also says something else. Once a spacecraft is deep in Jupiter's domain, there is no convenient, safe picking orbit where you just leave it forever. You either expend the energy to send it away, or you accept that its end will be a plunge into the planet. For robotic missions, that is fine. They are built with clear end dates. They do their science, then they die as planned. For a human mission, that kind of design is unacceptable. You cannot say when the ship is too damaged to trust we will just crash it if the crew is still on board. All of these probes also had one big advantage that a crewed mission does not have. They were expendable from the start. Voyager, Galileo, Juno, they were all designed with the understanding that they would not come back, and that they did not have to survive indefinitely. That changes everything. You can accept trajectories that clip through bad radiation zones if the science return is worth the damage. You can choose orbits that are fuel efficient but harsh. You can design systems to last long enough, not for decades. If a memory unit starts failing near the end of the mission, you live with it. If a sensor goes blind, you make do with the rest. The planning assumes from day one that the spacecraft will eventually be destroyed by Jupiter or by deep space. With humans, you do not get that freedom. You cannot design the mission around good science, then death. You need margins, backups, and exit strategies. You need systems that remain reliable even as radiation and time chew on them. You need orbits that are not just good for measurements, but good for survival. When you try to take the architecture and environment that worked for Galileo and Juno and overlay human safety requirements on top, everything inflates: the shielding, the redundancy, the fuel, the complexity. The basic shape of the mission stops looking like something you can launch and support with any realistic budget or technology, and it starts looking like a one-off mega project that still cannot promise a safe return. So if the probes already tell you the place is lethal and they only work because they can be thrown away, the next question is obvious. Can future technology break this pattern? If you had fusion drives, antimatter engines, giant laser sails, could you finally smash through all these limits and make Jupiter round trips routine, or is that just pushing the problem into a future that never quite arrives? Fusion rockets, antimatter drives, giant laser sails. It is easy to say future tech will fix this, but if you look closely at where that tech actually is, the gap between idea and hardware is huge. Fusion propulsion is the classic example. On paper, a fusion rocket with exhaust speeds of tens to hundreds of kilometers per second would smash through the Jupiter fuel wall. With that kind of performance, you could get enormous delta V without carrying absurd masses of propellant. You could cut travel times from many months to maybe a few weeks, reduce how long the crew sits in deep space and make the escape from Jupiter's gravity all look much less insane. But right now, we do not even have a single fusion power plant on Earth that reliably produces more energy than it consumes. And that is in massive, stationary buildings with huge support systems. Turning fusion from a lab experiment into a compact, rugged, SOAS-rated rocket engine is not just the next step, it is many steps, each of which takes time, money, and a lot of engineering failures along the way. Antimatter and beamed power sound even more dramatic, and they are, but in real engineering terms, they are nowhere near mission ready. Antimatter has an incredible energy density far beyond chemical or even nuclear fission and fusion. A tiny amount could, in theory, power a rocket with exhaust velocities high enough to make Jupiter round trips trivial on the fuel side. But we cannot produce antimatter in large quantities. The amounts created in particle accelerators are tiny, and storing even micrograms safely is extremely challenging. You need complex magnetic bottles to keep antimatter from touching normal matter and annihilating. Scale that up to the milligram or gram level you would want for a serious propulsion system, and you're completely beyond our current capabilities. Beamed power has a different problem. In principle, you could keep heavy reactors near the sun, then use huge laser or microwave beams to push lightweight sails or feed power to distant ships. In practice, that needs enormous, precisely aligned stations, and you have to keep beams locked onto a moving target across hundreds of millions of kilometers. Any misalignment or failure in that chain and your ship suddenly loses its main power source. Even if you imagine skipping ahead and saying, we have a drive with exhaust speeds around 100 kilometers per second, a level that makes the rocket equation far kinder, you're not done. High-performance propulsion solves part of the delta V problem and can shorten trip times, but it does not make Jupiter itself any less hostile. You still have lethal radiation belts that will fry unshielded humans in hours. You still have the fuel problem for attitude control, life support redundancy, and power systems. You still have a bottomless atmosphere with brutal winds and no solid surface, and an interior with pressures and temperatures that destroy any hardware you send too deep. A better engine means you carry less propellant and spend less calendar time in danger, which is a big win, but it does not erase the need for massive shielding, robust life support, and very high reliability across every subsystem for years. The environment does not care how good your engine is. You also have to be honest about timelines. Developing a radically new propulsion system like practical fusion or large-scale antimatter handling is not a 5-year project. It is decades of basic research, prototype building, failures, and gradual improvements. Then once you have a working propulsion unit, you have to integrate it into a human spacecraft, design full mission architectures around it, test them, and prove they are safe. That is more decades. By the time you have a mature, boringly reliable fusion drive that you trust for a 4 to 6 year Jupiter mission with human lives on the line, we will likely have fleets of robotic explorers, automated factories, and remote construction systems operating all over the outer solar system. At that point, the question becomes harsher. If robots can do the job, build infrastructure, and send back data without risking lives, why send people at all into a place with so many single-point catastrophic failures? This is why "we'll just invent X" is not something you can write into a serious mission plan. It is the same as saying "we'll just assume magic later." Real mission design has to be grounded in physics and technology that exist as tested hardware, or at least are so close that the risks are well understood. If your entire ability to get a crew home from Jupiter depends on a propulsion system that has never flown, or a material that has never been made at scale, or a power system that has never operated for a decade without major maintenance, you are not designing a mission. You are gambling with people's lives on hope and concept art. Until you have that full tech stack, from engines to shielding to life support to navigation, demonstrated in space and dull in its reliability, Jupiter remains effectively off limits for round-trip human travel. And even if you had that miracle engine tomorrow, there is still another hard limit that advanced drives do not erase. Gravity assists, moon bases, and clever orbital tricks can shave a little off the energy bill, but they cannot make Jupiter's gravity and radiation disappear. So what happens when you look for escape hacks, like using the moons as stepping stones or slingshotting off them to get out, and find out that all of those tricks barely dent the core problem? Jupiter's moons look like an escape ladder, but when you run the numbers, they are more like rungs on the same wall you're already stuck on. Jupiter has over 90 known moons, and the big four, Io, Europa, Ganymede, and Callisto, are large enough that you can seriously talk about landing on them. Their gravity is much weaker than Jupiter's. Ganymede's surface gravity is about 1.4 meters per second squared, Callisto's is around 1.2 meters per second squared, compared to Earth's 9.8 meters per second squared and Jupiter's roughly 25 meters per second squared at the cloud tops. In simple terms, you weigh a lot less there, and the speeds you need to take off and land are much lower. That makes them attractive as stepstones. You can picture a base on an icy moon, drilling into water ice, splitting it into hydrogen and oxygen, and using that as rocket fuel. That would help a lot with local operations, with hopping between moons, and maybe with topping off tanks before an escape burn. But even if you turn a moon into a big fuel depot, the main build does not vanish. You still have to escape Jupiter's gravity well as a whole, and that is where the huge energy cost sits. People then ask, can we use the moons themselves as slingshots the way we use planets? In principle, yes, you can use gravity assists off large moons like Ganymede or Callisto to adjust your trajectory. If you fly past a moon at the right angle and speed, you can steal a bit of its orbital energy, slightly raising or lowering your own orbit around Jupiter, or tweaking your path as you head out. That can save you some delta V, maybe hundreds of meters per second, in good cases maybe a kilometer per second or so. For small probes, that's a nice optimization, but compare that to the 60 kilometers per second escape speed at low Jupiter altitude, and the several to many kilometers per second out of total delta V you still need at the system level. Moon slingshots are small corrections in that context. They cannot provide the massive energy jump a big crewed ship needs to fully escape Jupiter, especially if you're starting from a deep orbit close to the planet rather than from way out near the moons already. Then there is the radiation problem again, this time for the moons. Io and Europa sit deep in Jupiter's radiation belts. Europa, the icy world everyone loves to talk about for possible life, is bathed in high-energy particles. An unprotected human on Europa's surface would receive a dangerous dose of radiation in a short time, hours to days. Ganymede and especially Callisto farther out are better, but they are still inside Jupiter's magnetosphere. Any long-term human base on these moons would need heavy shielding, likely regolith or ice piled up over habitats, plus buried structures, plus robust electronics hardened against radiation. Building that kind of infrastructure takes time, mass, and a lot of cargo flights. Every piece of that construction has to be launched from Earth or built by robots you sent earlier. And it all exists under the same big constraint. It is still living inside Jupiter's magnetic influence, not outside it. Even once that infrastructure exists, it does not magically fix the escape problem. A base on Callisto, for example, can produce fuel and reduce how much propellant you need to carry from Earth. That is valuable, but when a crewed ship lifts off from Callisto and wants to head back to Earth, it still has to climb out of Jupiter's gravity. The Moon's gravity is small, but the planet's is not. You've reduced one layer of the challenge, the local landing and takeoff, but the global one, the system escape, is still there. Your return ship still needs high delta V, still needs serious shielding for the time it spends transiting the system, and still needs long-term reliability for the engines and navigational hardware. What about the idea you hear so often, we'll use Jupiter itself as a gravity assist to escape? That works only if you never break into orbit in the first place. The classic Jupiter gravity assist, like Voyager used, assumes you come in fast on a solar orbit, swing around the planet once and leave again, still moving fast relative to Jupiter. You never pay the cost to become bound to Jupiter's gravity on a tight orbit. You just redirect your path around the Sun, stealing a bit of Jupiter's orbital energy. That is cheap and efficient for flybys, but it does not apply once you have slowed down and dropped into orbit. As soon as you pay the fuel price to be captured, those free energy tricks mostly disappear. To get back out, you now have to put energy back in, which means burning propellant. You can still get minor efficiency boosts using the moons, but nothing like the huge gain from a clean gravity assist flyby. So when you put all the escape hacks together, moon bases, in situ fuel production, slingshots off moons, clever orbital resonances, what do you actually get? You get optimizations at the edges. You can shave off a few kilometers per second of delta V. You can make landing and takeoff from local bodies more practical. You can reduce the amount of fuel you must carry all the way from Earth. These are all good improvements, but they do not change the core facts. The escape from low Jupiter orbit is still on the order of 60 kilometers per second. The radiation belts are still lethal. The mission is still multi-year. Your hardware must still survive for the entire span with almost no outside help. Moon tricks are like negotiating a small discount on a bill that is already far beyond what you can pay. For robotic missions, these optimizations are powerful tools. You can send fleets of probes that use moon assists, refuel from icy surfaces, and accept those radiation and reliability risks. Some will fail, some will succeed, and over time you build up a web of machines operating in the Jovian system. For human missions, the bar is much higher. Cutting 1 or 2 kilometers per second off a 60 kilometer per second problem does not suddenly turn an impossible round trip into a routine flight. It is still a mission where gravity, radiation, fuel, power, and human limits all stack in the same direction toward one conclusion. So after everything, gravity wells, fuel walls, radiation belts, bottomless atmosphere, brutal weather, exotic interiors, power constraints, multi-year timelines, navigation sensitivity, and the limited help from moons and assists, you reach the final question. When you step back and look at all of this together, what does physics actually say about a human trip to Jupiter with a promised return? So after everything you have heard, the obvious question is Jupiter too hard just because we are not trying hard enough? Or because the universe simply does not care what we want? The blunt answer is, physics does not care. Gravity, radiation, fluid dynamics, and the basic rocket rules are completely indifferent to human plans. Jupiter just happens to stack those things in the worst possible way for a round trip. It has a very deep gravity well. So the escape speed at the cloud tops is around 60 kilometers per second, roughly 134,000 miles per hour. It has lethal radiation belts powered by a huge magnetic field. It has a bottomless atmosphere instead of a solid surface, with pressure and temperature that ramp up until any normal material fails. And it sits far enough from the Sun that sunlight is only about 1/25 as strong as it is near Earth, which wrecks simple solar power plans. None of that is personal, it is simply where the numbers land, and those numbers line up against you. If you boil the whole situation down to a short list, the showstoppers are actually very clear. First, you need enough delta V to climb out of an environment where escaping from low orbit costs on the order of 60 kilometers per second, not the 11.2 kilometers per second you are used to from Earth. Second, you need enough shielding to keep humans alive in radiation zones, where an unprotected person can take a lethal dose in hours to days. Third, you need structures and vehicles that can tolerate violent winds, strong shear, and rising pressures without becoming so heavy that they are impossible to launch and recover. Fourth, you need life support that can run mostly on its own for 4 to 6 years without a major failure that you cannot fix with what you have on board. Each one of those points is already on the edge of what we can reasonably handle with current or near-term tech. When you put all of them together and demand that the same mission solve all 4 at once, the design quickly pushes beyond anything you would call sane or practical. This is why, when you look at actual missions, it is robots that get sent to Jupiter, not people. Robotic probes do not need air, water, food, or room to move around. They do not care about lifetime cancer risk from radiation. They do not suffer if a mission runs a few years longer. They can be built smaller and lighter, which makes the delta V problem easier. They can be hardened specifically against radiation, with thick local shielding and simple backup systems. If a probe flies through a region that would hit a human with tens of sieverts of radiation, it might glitch or slowly degrade, but it does not feel anything. And when the mission is over, or when the hardware is too damaged to trust, you can send the probe into Jupiter's atmosphere and destroy it. That is acceptable. Doing the same with a crewed ship is not. So when you picture going to Jupiter as a person, what you are really picturing with current technology is not a round-trip vacation. It is something closer to a one-way dive into a place you only leave in data form. A journey there and back again for humans sits in a gap. In theory, with perfect engines and perfect shielding and perfect life support, physics does not forbid it. In practice, with real materials, real engines, and real human bodies, the mission architecture breaks. The mass is too high, the fuel requirements are too large, the radiation doses are too intense, and the timelines are too long. That gap between what is technically allowed in equations and what engineering can actually build is exactly where the word impossible comes from in this context. Not impossible forever, but impossible for us, now, with what we can really field. It is important to be honest about that while also leaving the door open for the future. Calling it impossible today is not a prophecy that it will always be impossible. If one day we have fusion drives that are routine, not experimental, if we have materials that can self-heal under radiation and stress, if we have AI-driven life support systems that really can run for decades with vanishingly low failure rates, the trade-offs change. Travel times shrink, fuel loads drop, system reliability climbs, and maybe Jupiter becomes something a human can approach more safely, at least to its moons, maybe even closer. But to get there, you have to solve a long chain of hard problems and prove those solutions in space, for long durations, not just on slides or in animations. Right now, the honest verdict is simple and a bit harsh. A mission that tells a crew, "We will take you to Jupiter and bring you home safely," using technology that is even remotely close to what we have, is not telling the truth. The physics, the environmental, and the engineering limits all pile up on the same side. Jupiter is, at this moment in history, one of the most spectacular and scientifically rich places we can study, and at the same time one of the clearest examples of a destination that is effectively one way for humans. We can look at it, orbit it with robots, drop probes into it, and learn from it, but we do not send people there and expect them to come back. So the real frontier around Jupiter for now is not how soon can we fly tourists there, or this is how far can we push machines in our place. Until the day we have engines, materials, and life support that can laugh at deep gravity wells and lethal radiation, Jupiter stays on the list of places where human footprints only exist in stories, not in flight plans. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.